Hello, welcome back. Wherever you are right now, and I mean that as specifically as I can, wherever you've arranged yourself tonight, I'm glad you're here. Maybe it's the same spot as always, that particular corner of the bed, or that end of the couch that has quietly become yours through some slow negotiation with habit and gravity. Maybe it's somewhere new, a different city, a different room, the unfamiliar geometry of a place you haven't slept in before. It doesn't matter. You're here now, and that's enough. Go ahead and get comfortable. Take a moment and actually do it. Adjust whatever needs adjusting. Pull whatever needs pulling. Tonight's conversation is a long one, in the best possible sense. There's nowhere to rush to, and the topic we're going to explore has been waiting a very long time for us to notice it. A few extra seconds to find the right position won't change anything. You don't need to remember any of this in the morning. You don't need to take notes or look anything up afterward or be ready to explain it to someone else. This is a place for learning that happens in the soft, receptive part of the mind rather than the sharp, note-taking part. Things will settle in the way they settle. And if you drift off before we're finished, that's not just acceptable. It's the whole design. If you're finding your way here for the first time, welcome. This is Late Space. We take big ideas and we hold them gently, at a pace that matches the hour. If you like the company on nights like this, a like or a subscribe would mean a great deal. It helps other people find this place on their own sleepless evenings. But do it tomorrow, or don't do it at all. Right now, just settle. Tonight, we are going to talk about one of the most significant things that has happened in science in a very long time. Not the most certain thing. Not the most proven thing. In fact, part of what makes it so worth discussing carefully and slowly, in the dark, at this hour, is precisely that it sits in that particular zone of scientific inquiry where something extraordinary has been glimpsed, but not yet confirmed, not yet resolved, not yet handed down as settled fact. In April of 2025, a team of astronomers at the University of Cambridge announced something that made front pages around the world, and then was quietly, rigorously, respectfully contested by other scientists, and is now sitting in the middle of one of the most alive and productive debates in the history of the search for life beyond Earth. They announced that a telescope, the James Webb Space Telescope, the same extraordinary golden mirrored instrument we've discussed in previous conversations, had detected something in the atmosphere of a planet 124 light-years away. Something that on Earth is produced almost exclusively by living things. The planet is called K2-18b, and the headline number was 99.7%. Tonight, we are going to understand what that number actually means. Not just what it sounds like, which is dramatic enough, but what it actually is, technically, where it comes from, what it can and cannot tell us, and why, even surrounded by genuine scientific debate about whether the signal is real, the story of K2-18b is one of the most remarkable things our species has ever attempted to learn. Close your eyes when you want to. We'll go slowly. Let's begin. Let's start not with the discovery, but with the question underneath it, because the question is older than any telescope and more fundamental than any single detection. Are we alone? It's the question that sounds almost too simple, too obvious, too large to actually address directly. It's the kind of question children ask and adults nod at thoughtfully, and nobody quite answers, because the honest answer for most of human history has been, we don't know, and we don't have a way to find out. For a very long time, this was not for lack of curiosity. It was for lack of tools. The universe is large in a way that defeats the imagination, and for most of our history as a species, we didn't even know that the universe contained other solar systems at all. The stars were distant, yes, but whether they had planets, whether those planets had oceans or mountains or anything at all, was entirely beyond our ability to know. That changed in the 1990s, and changed rapidly. The first confirmed planets orbiting other stars were detected by measuring the tiny gravitational wobbles their mass induced in their parent stars, a technique called radial velocity. Sensitive and patient, and extraordinarily clever. Then came the transit method, which looks for the slight dimming of a star's light when a planet passes in front of it, briefly blocking a small fraction of the starlight on its way to our telescopes. This method, refined and scaled up by the Kepler Space Telescope, revealed thousands of planets. It turned out the galaxy is not merely inhabited by planets, it is full of them. Most stars, it appears, have at least one planet, and many have several. But detecting planets is one thing. Understanding what they're like, whether they're rocky or gassy, hot or cold, dry or covered in water, requires a different level of observation. And asking whether any of them might be alive requires something further still. The ability to examine their atmospheres, to look at the light filtering through their thin shells of gas, and to read in that light the chemical fingerprints of whatever molecules are present. This is called atmospheric spectroscopy, and it is, in every meaningful sense, one of the most extraordinary things human beings have ever learnt to do. It is the art of reading a planet's chemistry from 124 light-years away by studying the shadow its atmosphere casts in the light of its star. And it is what Webb was built, in part, to do. Let me tell you about transit spectroscopy, because it's one of those techniques that, when you understand how it works, produces a particular kind of quiet astonishment, not at the discovery it enables, but at the ingenuity of the method itself. When a planet passes in front of its star, crosses the face of the star, as seen from our vantage point, a small fraction of the star's light is blocked. The planet is opaque. So far, so ordinary. But the planet's atmosphere is not opaque. It's thin and partially transparent. And crucially, different molecules in the atmosphere absorb different wavelengths of light. Methane absorbs some wavelengths, carbon dioxide absorbs others, water vapor absorbs others. Each molecule has a kind of chemical fingerprint, a specific pattern of wavelengths it prefers to soak up as light passes through it. So during a transit, as starlight filters through the thin shell of the planet's atmosphere on its way to our telescope, certain wavelengths arrive slightly dimmer than others, depending on which molecules are present to absorb them. By looking carefully at which wavelengths are depleted, by taking what's essentially a spectrum of the filtered starlight and comparing it to what the unfiltered starlight looks like, you can read out the composition of the atmosphere. You are, quite literally, tasting the air of another world from 124 light-years away. Not with instruments on that world, not with a probe sent through that atmosphere, just by carefully analysing light that has done the tasting for you on its way across the gulf of space. It's a bit like holding a piece of coloured glass up to sunlight and noticing which colours are missing on the other side. The glass tells you about itself by what it takes from the light. The atmosphere of a distant planet tells you about itself the same way. Webb is extraordinarily well suited to this technique. Its large mirror, nearly 7 meters across, made of 18 hexagonal segments of gold-coated beryllium, deployed in deep space at a point where Earth's own atmospheric interference doesn't muddy the signal, gives it the light-gathering power to detect the subtle, delicate chemical fingerprints of molecules present in parts per million in the atmosphere of a planet 100 light-years away. It is, by any honest reckoning, a miraculous instrument. Not miraculous in the supernatural sense, but miraculous in the older sense of the word, something that produces wonder. Now let me tell you about the planet. Because K2-18b, even before the April 2025 discovery, was already one of the most interesting exoplanets we had ever found. It was first detected in 2015 by the K2 mission, an extended, redesigned version of the original Kepler Space Telescope, operating after 2 of its 4 reaction wheels failed, and engineers devised an elegant workaround that let it continue doing science with a different pointing strategy. K2-18b transits its star, a red dwarf, cooler and smaller and dimmer than our own Sun, roughly every 33 days. Through the transit signature and through follow-up measurements of the star's radial velocity wobble, astronomers worked out the basic facts. K2-18b is a sub-Neptune, a type of planet more massive than Earth but smaller than Neptune. It's about 8.6 times the mass of Earth and about 2.6 times the radius. This puts it in a size range that doesn't exist in our own solar system, which skips directly from rocky planets no larger than Earth to ice giants the size of Uranus and Neptune, with nothing in between. In the wider galaxy, however, sub-Neptunes are extraordinarily common. The most common type of planet we've found, in fact, and yet we have no local example to help us understand exactly what they're like, which makes each one we study in detail correspondingly more valuable. K2-18b orbits its red dwarf star at a distance of about 0.16 astronomical units, much closer than Earth orbits the Sun. But red dwarf stars are considerably cooler and less luminous than our own star, so at that distance, the planet receives roughly the same amount of energy from its star as Earth receives from the Sun. K2-18b sits in what astronomers call the habitable zone, the just right region around a star where temperatures might allow liquid water to exist on a planet's surface, not so hot that it evaporates away, not so cold that it freezes permanently. Habitable zone, a phrase that sounds modest and technical but carries an enormous weight of implication. And K2-18b is there, in it, orbiting at the right distance, receiving roughly the right amount of heat. Now here is where the story starts to become truly interesting, and I want to take it slowly because the ideas build on each other. In 2021, Nikku Madhusudhan, a professor of astrophysics at the University of Cambridge, originally from India, one of the world's leading experts in exoplanet atmospheres, proposed a new category of planet that nobody had formally described before. He called them Hycean worlds. Hycean is a blended word, combining hydrogen and ocean. The idea is this: a planet with a mass somewhat larger than Earth's, but smaller than Neptune's, with a deep global ocean of liquid water covering the entire surface, and above that ocean a thick atmosphere made primarily of hydrogen rather than the nitrogen-oxygen mix that blankets our own world. This is, if you stop to picture it, genuinely alien. An entire planet, oceanic from pole to pole, with no land anywhere, no continents, no beaches, just an endless rolling planetary sea reaching all the way around, and above it a thick hydrogen sky, and beneath it an ocean that might be hundreds of kilometers deep. It sounds like something from a novel. But Madhusudhan and his colleagues worked out the physics carefully, and Hycean worlds are not only possible. Given the composition and density of many sub-Neptunes that have been found, they may actually be common. The universe may be full of entirely water-world planets, wrapped in hydrogen atmospheres, quietly orbiting their stars. And here is the remarkable thing about Hycean worlds from an astrobiological perspective, that is, from the perspective of thinking about where life might exist. Because they're covered in liquid water, and because liquid water is one of the foundational requirements for life as we understand it, they are potentially habitable. Not just possibly habitable around the edges, in some marginal way. Potentially, genuinely, deeply habitable. Because there's water everywhere, all the time, on a global scale, at conditions that might allow complex chemistry to proceed. Moreover, because the hydrogen atmosphere is lighter and more transparent than a heavier atmosphere, the scale height of the atmosphere, the depth at which atmospheric gases are distributed, is larger. This makes it easier for our telescopes to detect the chemical fingerprints of whatever is in there. Hycean worlds, in a beautiful piece of scientific serendipity, might not only be habitable, but also unusually easy to study from a great distance. Madhusudhan and his colleagues proposed, in 2021, that K2-18b was a promising Hycean candidate. The size was right, the density was consistent with a deep ocean, and the orbit put it in the habitable zone. The hypothesis was testable, using Webb. Wherever you are, I hope you're comfortable. We're in the middle of the story now. The planet has been found and characterized. The theory has been proposed. The telescope is in space. Let's see what happened next. In 2023, Webb observed K2-18b as it transited its star. The data came back, and Madhusudan's team analysed it with considerable care, looking for the chemical fingerprints of whatever molecules were present in the atmosphere. They found carbon dioxide. They found methane, both present in a hydrogen-rich atmosphere, consistent, they noted, with a Hycean world, where an ocean surface below might be driving a particular chemical balance that mimics, in some ways, the chemistry of our own Earth's atmosphere as filtered through an ocean. And there was something else. A tentative signal in the data, at certain wavelengths, that looked like it might be consistent with the presence of dimethyl sulfide. Dimethyl sulfide, DMs for short. A molecule with a distinctive smell is part of what gives the ocean its smell, actually. That particular salty, slightly sulphurous quality you notice when you're near the sea on a breezy day. On Earth, dimethyl sulfide is produced almost exclusively by living organisms, specifically by marine phytoplankton, the microscopic, single-celled creatures that populate the surface waters of our oceans in staggering numbers, quietly photosynthesizing and releasing dimethyl sulfide as a metabolic byproduct. Almost exclusively by living organisms. Not quite exclusively. That distinction matters, and we'll come back to it. But on Earth, in our atmosphere, if you find dimethyl sulfide, it is almost certainly there, because something alive put it there. The 2023 detection was tentative. A hint, not a confirmation. The signal was in the near-infrared, in a wavelength region where methane also absorbs, making it hard to cleanly separate the two. The team reported it carefully, noting that it might be DMs, but that the confidence was not high enough to say so definitively. They called for further observations. Those further observations came. And in April 2025, Madhusudan's team published again. This time, they had used a different instrument on Webb, the MIRI spectrograph, which looks in the mid-infrared rather than the near-infrared. MIRI sees at longer wavelengths, where dimethyl sulfide and its chemical cousin dimethyl disulfide have their most distinctive absorption features, and where the overlap with methane is less severe. The new analysis found a signal, not just for dimethyl sulfide, but possibly for dimethyl disulfide, DMDs as well, both from the same family of sulfur containing organic compounds. And the confidence level was 99.7%. Let me tell you what that number means. Because in scientific reporting, confidence levels have a specific technical meaning, and it's different from the everyday sense of the word. When scientists report a confidence level of 99.7%, or equivalently, when they say the result is at what's called 3 sigma significance, they mean this: if the signal were not real, if there were nothing actually there, and what they were detecting was purely random noise, then the chance of observing data this extreme, or more extreme, purely by statistical accident, is 0.3%. 0.3%. Not the probability that life exists on K2-18b. Not the probability that DMs is present. The probability, under the specific assumption that there is no DM signal at all, of observing data this strong or stronger by chance alone. This is an important distinction, and Madhusudan and his team made it carefully. 3 sigma is the conventional threshold for claiming a detection worth taking seriously in physics and astronomy. It is not the 5 sigma threshold typically required for an extraordinary claim, a discovery. It is the level at which you say, this is real enough to report, real enough to take seriously, real enough to do more work on. And the team was at pains to be clear, they were not saying they had found life on K2-18b. They were saying they had found a signal at a level of confidence that warrants serious attention, that is consistent with the presence of molecules which, on Earth, are produced by living things. The claim was enormous enough on its own. The planet could be alive, they said, or it could be doing chemistry we don't yet understand. But the signal is there, and it needs to be understood, the world responded as you might expect. Headlines about alien life. Breathless summaries. The phrase paradigm shift appeared, as it does whenever something like this surfaces. Madhusudan himself used that phrase, carefully, in context, in a specific sense, and it ricocheted around the internet somewhat detached from its qualifications. And then the scientific community did what the scientific community does when something extraordinary is claimed, which is the thing the scientific community should always do. They scrutinized the data. This is not hostility, it is not skepticism in the cynical sense. It is, in the deepest sense, the most respectful possible response to a remarkable finding. Extraordinary claims require extraordinary evidence, as Carl Sagan famously articulated, and the process of science is specifically designed to test claims against every possible alternative before accepting them. Several independent teams went back to the Webb data. They reanalyzed it from scratch, with different software, different methods, different assumptions about how to process and interpret the raw numbers coming down from the telescope. And what they found complicated the picture considerably. One set of reanalyses by multiple independent groups published throughout 2025 found that the MIRI data, the mid-infrared observations that were the basis of the 99.7% claim, was considerably more sensitive to the precise choices made during data reduction than the Cambridge team's analysis had indicated. Small differences in how the raw numbers were binned and processed led to large differences in what the resulting spectrum looked like, and consequently to very different conclusions about what molecules were present. In the majority of alternative analyses, the specific signal attributed to DMs and DMDs did not reach statistical significance. In the bluntest of these reanalyses, published in late 2025, a team of researchers concluded directly in their paper's title that K218b does not meet the standards of evidence for life. They found that 87.5% of their alternative data processing approaches did not reproduce the DM signal, and that the mid-infrared data appeared to be contaminated by instrumental effects, what scientists call red noise, a systematic drift in the readings that can mimic a genuine signal if you're not careful. Other teams raised a different concern, which is conceptual rather than instrumental. On Earth, the concentration of dimethyl sulfide in our atmosphere is measured in parts per billion. Tiny, a trace. The amount that marine phytoplankton contribute to our atmosphere across all the world's oceans is enough to smell near the sea, but not enough to be easily detected from light years away. The inferred concentration of DMs in K218b's atmosphere from Madhusudan's analysis was in parts per million. That's roughly 1,000 times more concentrated than the DMs in Earth's atmosphere. And this raises an uncomfortable question. Even if life exists on K218b, even if it's a global ocean teeming with marine microorganisms of some form, could biology really produce DMs at concentrations 1,000 times higher than all of Earth's oceans combined? Some modelling suggests perhaps yes, the conditions on a Hycean world might be different enough from Earth's, that the chemistry works differently, concentrations build up differently, the physics of how gas escapes the atmosphere and is replenished are different. But the uncertainty is real and significant. And then there is the question of whether DMs requires life at all. Because in 2024, a separate scientific team reported something that cut directly across the biosignature argument, they found dimethyl sulfide on a comet. A cold, lifeless comet, not produced by any biological process, but assembled through the chemistry of ices and organic compounds in the cold of deep space. And in 2025, another team reported the discovery of dimethyl sulfide in the interstellar medium, in the gas and dust between the stars, far from any planetary system, in a region where life as we understand it absolutely does not exist. Dimethyl sulfide, it turns out, is not exclusively a product of life. It can be produced abiotically, without biology, under the right conditions. The question is whether those conditions exist in K218b's particular environment, and whether they could produce the concentrations that might explain the MIRI signal. As of the end of 2025 and into 2026, this question remained genuinely open. Madison's team maintained that the signal was real and that abiotic explanations faced their own difficulties. DMS is chemically fragile, destroyed relatively quickly by ultraviolet radiation, and maintaining high concentrations of it in an atmosphere requires continuous replenishment. On Earth, that replenishment comes from biology. Whether some abiotic mechanism could maintain it at the inferred levels on K218b, they argued, had not been convincingly demonstrated. Their critics maintained that the data itself was not robust enough to support the conclusion, regardless of what was producing the signal, that the first step, confirming the signal as real and not an artifact, had not yet been satisfactorily established. The debate, as of now, is ongoing, active and conducted with the collegiality and rigour that science, at its best, manages to bring to questions of this magnitude. Wherever you are, I hope you're still comfortable. Let's just breathe here for a moment, because I want to acknowledge something. This story, told at this level of detail, might feel like it undermines the headline, like the exciting discovery turned out to be less than it seemed, but I'd like to suggest the opposite reading, and I think it's the honest one. What we have right now tonight is this: an extraordinary machine that humanity built and launched into space has detected a signal in the atmosphere of a planet orbiting another star 124 light-years away that is at minimum consistent with the presence of molecules that on Earth we associate with life. That signal is contested. Its origin is uncertain. The data processing choices that reveal it are under scrutiny. The concentrations don't quite fit our expectations if biology is the source. Abiotic pathways exist and are being investigated. And yet, the signal is there. Something in the atmosphere of K218b is absorbing light at specific wavelengths in the mid-infrared, and that something has not been definitively explained by any other molecule. The debate is not between we found life and there's nothing there. It's between this signal is most plausibly DMs or DMDs, and the signal might be caused by other molecules, or by instrumental artifacts. The planet is still in the habitable zone. It is still a plausible Hycean world. The methane and carbon dioxide detected in 2023, with considerably more confidence, remain in the atmosphere. We are not standing in the light of a confirmed discovery. We are standing at the threshold of a question. The question, arguably, that science has ever been equipped to answer. And we have better tools for asking it than any generation before us has ever had. That is not a small thing. That is a remarkably large thing, quietly disguised as an ongoing scientific dispute. Let me tell you about the man at the centre of this. Niku Madhusudan. He was born and raised in India, studied physics, came to the United States for graduate work, and eventually settled at Cambridge, where he has spent over a decade thinking carefully about the atmospheres of exoplanets and what they might tell us about habitability and life. He is, by reputation, both intellectually rigorous and genuinely passionate about the question his work is trying to answer. Not the narrow technical question of what molecules are in which spectra, but the enormous human question underneath it all. The Hycean world concept he proposed in 2021 was not the product of idle speculation. It came from a careful analysis of what kinds of planets were the most promising targets for atmospheric biosignature searches, what kinds of planets might actually host the conditions for life, and what kinds of planets Webb would be able to study effectively. It was a piece of synthetic, integrative scientific thinking, combining observations, theory, and instrumentation strategy into a research program that asked the right questions with the right tools. When the April 2025 results came out and were met with skepticism from independent teams, Madhusudan did not retreat or become defensive in the way that might be understandable given the public pressure surrounding the claim. He acknowledged the debates, maintained his reading of the data, and called for more observations. This is precisely how science is supposed to work. The claim is made carefully, it is contested vigorously. The original claimants defend their analysis, more data is gathered. Eventually, the evidence either accumulates in favour or doesn't. Confidence either grows or the claim is revised. There is something almost classical about it. The scientific method, which we often describe in textbook terms as a tidy procedure, is in practice more like a long, public, passionate conversation between people who all care deeply about getting the answer right, and who disagree, sometimes sharply, about what the current evidence actually says. Madhusudan and his critics are both part of this conversation, and both are necessary. Let me tell you something about the star that K2-18b orbits, because the star is relevant in ways that are not obvious at first. K2-18 is a red dwarf, an M-type star, smaller, cooler, and dimmer than the Sun. Red dwarfs are the most common type of star in the galaxy. Roughly 70% of all stars are red dwarfs. Which means that if planets around red dwarfs are habitable, if life can arise and persist in those systems, then most of the inhabited worlds in the galaxy, if there are any, are probably orbiting red dwarfs. This is encouraging in a way, but there are complications. Red dwarfs are energetic in their youth in a specific and problematic way. They flare, more than the Sun, more intensely, more frequently. Young red dwarfs throw off ultraviolet and X-ray radiation in powerful bursts that can strip away planetary atmospheres, damage the chemistry of surface environments, and generally make the early history of any planet around them somewhat hostile to the kind of slow, patient chemistry that preceded life on Earth. For K2-18b's specifically, whether the radiation environment from its red dwarf host is compatible with the persistence of an ocean, with the development of life, with the maintenance of biosignature gases in the atmosphere, these are active research questions. Some models suggest that the thick hydrogen atmosphere of a Hycean world might actually provide considerable protection, acting as a buffer between the star's radiation and the ocean surface below. Others are less optimistic. The star's radiation also directly affects the chemistry of DMs in the atmosphere. Ultraviolet light destroys DMs fairly quickly. It's photochemically unstable, meaning it breaks down when hit by sufficiently energetic photons. This is both a problem and an argument. It's a problem because it means any DMs in the atmosphere needs to be continuously replenished. But it's also, Madhusudan and colleagues argue, a point in favour of the biological interpretation. If DMs is being destroyed continuously by the star's radiation, and yet maintains detectable concentrations, something must be producing it at a substantial rate, and the question is what? They argue that abiotic processes that produce DMs, the kinds that make DMs in comets for instance, do not replenish it quickly enough to explain the concentrations observed. Biology, on the other hand, is a continuous, self-sustaining chemical process that could plausibly do so. This argument is not decisive. The critics point out that we don't yet know enough about the abiotic chemistry of hydrogen-rich atmospheres in the specific conditions of a Hycean world to rule out non-biological sources. It's an honest disagreement about where the burden of explanation lies. Let me take you back to what this would actually look like, if K2-18b is what Madhusudan and his team suspect it might be. Light years from Earth. In the direction of the constellation Leo, a red dwarf star, cooler than the Sun, glowing in the infrared rather than the warm yellow-white of our own sky. Orbiting that star, at a distance somewhat closer than Mercury, orbits our Sun, but receiving about the same energy. Because the star is so much dimmer. It is a world. It is larger than Earth. You can feel that in the gravity. not crushing, but noticeably heavier. But it is water world without qualification, pole to pole, horizon to horizon in every direction, a planet-wide ocean that goes down for hundreds of kilometers before you'd reach any kind of solid surface beneath it, if there is one at all. There is no land, no mountains to speak of, no continents, no rivers, no beaches. Just water, and above it the atmosphere. And that atmosphere is different from ours. It's thicker, and it's mostly hydrogen rather than nitrogen. The sky through it would not be our blue, it might look strange to human eyes, different colours scattered differently through a different molecular composition. The star, smaller and redder than our sun, would not look like our daylight. It would be dimmer, ruddier, and it would pass overhead more quickly because the planet orbits faster. And in that global ocean, in this picture, something lives. Not complex life, nothing like fish or corals or anything with size or structure we could easily recognize. Microbial life, most likely, if life at all. Single-celled organisms, floating in the upper layers of the ocean where there's enough light and enough chemistry to drive metabolism. Something like marine phytoplankton, analogous to but not identical to the creatures that make dimethyl sulfide in our own oceans. Doing what life does, taking in energy and chemicals, doing chemistry with them, releasing byproducts. And one of those byproducts, one of the molecules drifting up from those microbial metabolisms into the hydrogen atmosphere above, is dimethyl sulfide. Rising, dispersing, gradually being broken down by the star's radiation, being replenished continuously from below, accumulating in the atmosphere at concentrations that are faint by everyday standards but large enough, against the backdrop of the planet's hydrogen sky, to leave a mark in the light as the planet transits its star. And that mark, that tiny, contested, argued-over dip in the spectrum of a dim red star 124 light-years away, is what a golden mirrored telescope in space, built by tens of thousands of people over decades, detected and measured. And reported. And we are now sitting with it, carefully, trying to decide what it means. I want to tell you about biosignatures more broadly, because K218b is not an isolated story. It's the most visible part of a much larger scientific project that is quietly one of the most ambitious things our species has ever attempted. A biosignature is, in its simplest definition, a sign of life that can be detected remotely. Not life itself, not a cell, not an organism, not anything you could hold in your hand, but a marker, a chemical, a physical signal, a pattern that is either only produced by life or is produced in quantities or configurations that are only explained by life. On Earth, oxygen is a biosignature. Our atmosphere is about 21% oxygen, and that oxygen is entirely the product of billions of years of photosynthesis by plants, algae, and cyanobacteria. Without continuous biological production, the oxygen in our atmosphere would react with rocks and other chemicals and disappear on geological timescales. An alien telescope, looking at Earth's light spectrum, would see the oxygen and could infer that something biological was generating it continuously. Methane, in combination with oxygen, is an even stronger biosignature. The two react with each other. If both are present in an atmosphere simultaneously, something must be producing each of them faster than the other can destroy it, and the most likely explanation is biology, because life is the most plausible source of continuous methane production in the presence of an oxidizing atmosphere. Ozone, nitrous oxide, phosphine, dimethyl sulfide, these are all biosignature candidates, molecules whose presence in a planetary atmosphere, under certain conditions, would be difficult to explain without invoking life. The challenge is that none of them is unambiguous. Every biosignature gas can, in principle, be produced abiotically. Oxygen can be liberated from water by ultraviolet photolysis. Methane seeps from geological vents. Phosphine has been found in the clouds of Venus, where nobody seriously argues for life. DMs, as we now know, shows up in comets and in the interstellar medium. What biosignatures provide is not proof, but evidence. Probabilistic evidence, to be interpreted in the context of everything else we know about a planet, its size, composition, temperature, orbit, the nature of its star. The meaning of a biosignature depends on context, and the better we understand the context, the more or less meaningful any specific signal becomes. This is why the debate about K218b is not just an argument about one signal on one planet. It is a debate about how to do astrobiology in an era when we actually have the instruments to search for life beyond Earth, how to set evidentiary standards, how to distinguish signal from noise, how to balance the desire to announce a remarkable finding against the obligation to be certain before claiming it. These are not easy questions. They're being worked out in real time in the scientific literature by people who are genuinely doing their best and who genuinely disagree about the answers. Wherever you are, I hope you're comfortable. The night is deepening. We're past the harder parts of the science. What's left is the feeling of all of this, and that feeling is worth taking slowly. Let me tell you something about the pace of this discovery that I find genuinely moving. The James Webb Space Telescope was proposed in the 1990s. It took decades to build, longer to launch than planned, and longer still to deploy and calibrate. Thousands of engineers, scientists, programmers, administrators, and support staff contributed to making it work. The total cost was roughly $10 billion over 30 years. Its primary mission was to study the early universe, the first galaxies, the first stars, the universe in its infancy. The study of exoplanet atmospheres was always part of the plan, but not the headlining purpose. And yet here we are, 3 years after launch, and Webb has already detected carbon dioxide and methane in the atmosphere of a habitable zone planet. It has detected a signal that might be dimethyl sulfide. It has, in other words, moved the question, are we alone, from the category of unanswerable philosophical speculation into the category of active scientific investigation with current data. 30 years ago, we didn't know planets around other stars existed. 20 years ago, we knew they existed, but couldn't characterize them at all. 10 years ago, we could characterize their basic properties, but couldn't read their atmospheres. Today, we are arguing about whether a specific biosignature molecule has been detected in a specific planet's atmosphere at 3 sigma confidence. The argument itself is a measure of how far we've come. A decade ago, we wouldn't have had the data to argue about. Now let me tell you what comes next. Because the story of K218b is not finished. It's barely started. The path forward is straightforward to describe, if not simple to execute. More observations. More transits. More light collected. More spectra analysed. More independent teams working with the same data and different teams working with new data. The contested MIRI signal needs to be either confirmed or shown to be instrumental noise through repeated observations with improved techniques. Other molecules need to be tested as alternative explanations for the signal, with the growing library of molecular spectral data that experimental chemists are continuously adding to. And then, if the DM's signal is confirmed, if it holds up under the scrutiny of additional observations, if the alternative explanations are progressively ruled out, the next question becomes, can we distinguish between a biological and an abiotic source? This is harder. It may require understanding the broader chemistry of K218b's atmosphere well enough to say whether the concentrations make sense given what's known about abiotic pathways. It may require theoretical modelling of what a microbial biosphere on a Hycean world would actually produce, and how those predictions compare to what's observed. There are other planets being studied too. K218b is the most prominent habitable zone sub-Neptune that Webb has examined for biosignatures. But it's not the only candidate. The same team has studied another planet called TOI 270Ds, a similar sub-Neptune with the potential to be another Hycean world. Other observing teams are targeting other systems. A new generation of still larger telescopes currently under construction, the extremely large telescope in Chile, the Nancy Grace Roman Space Telescope in orbit, will, over the next decade, add new capabilities to this search. What we're building, slowly and with genuine difficulty, is not just a single detection, it's a methodology. A way of searching for life at interstellar distances that can be applied systematically to world after world until either the signals accumulate into something undeniable or the silence becomes its own kind of answer. Either outcome, honestly, would be extraordinary. Let me tell you why the silence would also be extraordinary. If we searched 100 habitable zone planets with the sensitivity of Webb and found no biosignature signals anywhere, not just on K218b, but nowhere, in none of the atmospheres we examined, that would be a profound scientific result. It would suggest that either the conditions for life are far rarer than we might have hoped, or that life, while perhaps common at the microbial level, doesn't produce the specific chemical signatures we're looking for in ways we can detect from this distance, or that there is something fundamentally unusual about life's emergence, something we don't yet understand, that makes planets like Earth genuinely rare among the billions of habitable zone worlds in the galaxy. This is sometimes called the Fermi paradox in its observational form. The galaxy is old, and it's full of planets, and yet we have found no signals of life anywhere. Every null result, every careful, sensitive observation of a habitable planet that comes back showing only abiotic chemistry adds a small weight to one side of that scale. And every signal, however contested, however uncertain, adds a small weight to the other. Right now the scale is extremely uncertain. One possibly detected biosignature molecule at 3 sigma confidence in one planet, contested by independent analysis. We are not yet in a position to say where the balance lies. We have collected almost no evidence, in statistical terms, on either side, which is the right and honest way to describe the moment we're in, the very beginning of the search. The very first tentative steps into a question that will likely take decades to answer, if it can be answered at all. And K218b is the first step. Let's come down slowly now toward the quiet end of the evening. Here is what is true, as carefully as I can state it tonight. There is a planet, 124 light-years away, in the habitable zone of a red dwarf star, that is consistent with being an ocean world covered in liquid water under a hydrogen-rich atmosphere. The James Webb Space Telescope has detected methane and carbon dioxide in its atmosphere with high confidence. It has detected a signal in the mid-infrared that the Cambridge team interprets as possibly being dimethyl sulfide or dimethyl disulfide, molecules that on Earth are produced almost exclusively by life. That signal was reported at 99.7% confidence, 3 sigma, which is the standard threshold for a detection worth taking seriously, but not the higher bar required to call it a confirmed discovery. Independent teams have reanalyzed the data and found the signal to be less robust than claimed, possibly affected by instrumental systematics and possibly attributable to other molecules. The debate is ongoing and unresolved. And underneath all of that, the larger truth, we now have the tools to actually look for life on other planets. Not theoretically, not in some distant future, not as a thought experiment. Now with Webb, with the observations being taken and the data being analysed and the arguments being made, right now in this decade, we are, for the first time in the history of our species, actually doing this. That is the thing worth holding on to as you drift. Not a confirmed discovery, not certainty, but the extraordinary, almost incomprehensible fact that we live in the first generation of humans who can seriously, rigorously, quantitatively search for life beyond Earth. That the question we have always asked, but one so big it sounds like mythology, the one that goes back to every human being who ever looked up at the stars on a night just like this one, is now a question science is actively attempting to answer. And somewhere, in the data already collected, in the observations already made, in the photons that have already been caught by a golden mirror 1.5 million kilometers from Earth, the answer might already be waiting, already encoded in the numbers, already there in the light from a distant blue-green water world, whispering something so quiet and so extraordinary that we need better instruments and more transits and more time to hear it clearly. I want to leave you with something Niku Madhusudan said, not in the technical language of a scientific paper, but in the language of someone who has spent decades thinking about a question that most people don't allow themselves to think about seriously. He said that if this is confirmed, if K218b's atmosphere really does contain the chemical fingerprints of biological activity, it would mean that life is not a singular accident, not a freak occurrence on one small rocky planet orbiting one ordinary star. It would mean that the universe makes life routinely in the kinds of places where the conditions allow it. That life is not the exception, but in some sense the rule. And even if K218b turns out to be a false alarm, even if the signal dissolves under future scrutiny, even if the DMS is abiotic or the data was contaminated, the question doesn't go away. There are hundreds of billions of stars in this galaxy alone. Hundreds of billions of galaxies in the observable universe. The habitable zone planets number in the trillions. The question of whether any of them hold life is not a question that can be settled by one ambiguous signal on one planet. It will be settled by the slow accumulation of observations, one world at a time, over years and decades and perhaps generations. We are at the beginning. That's not a small thing to sit with at the end of a long night. Close your eyes, if they're not already closed. Somewhere right now, or rather 124 light-years of light travel time ago, which is as close to now as astronomical distances allow, a planet is orbiting its red star. Every 33 days it passes in front of that star, briefly, and its atmosphere filters the starlight. And in that filtered light there are features, signals, chemical fingerprints, a record of whatever is happening in that hydrogen sky above whatever ocean lies below. That signal has already left that planet. It has already been travelling toward us for 124 years. It arrived. Webb caught it. Madhusudan's team measured it. Other teams measured it differently. The argument continues. Somewhere in all of that, perhaps, is an answer. Not to everything, not to all of it, but to the smallest, most specific version of the oldest question. Is there anyone else? We don't know yet. But we're looking. With our best instruments and our most careful minds and our most rigorous arguments about what counts as evidence. Looking, as we've always looked, at the lights in the dark. Rest now. The universe will still be there in the morning. The planet will still be orbiting. The signal will still be contested. The scientists will still be arguing, carefully and productively, towards something that might one day be called an answer. And you will still be here, on a small, improbable, living planet, 124 light-years from a question that no one has yet been able to answer. That is a beautiful place to fall asleep. Thank you for spending tonight here. Thank you for caring about this question, even at this hour, even when you didn't have to. Thank you for being the kind of person who lies in the dark and wonders whether anyone else is out there. Sleep well. And whatever the answer turns out to be, however this story resolves, in the coming years, in the observations not yet taken, in the papers not yet written, tonight, you were part of the wondering. Good night.